Hello, everyone. I'm excited to share my work in analyzing and designing complex acoustic environments, computational and AI-driven approaches. My name is Alaa Algargoosh, and I am an assistant professor in architecture at Virginia Tech. And today I'll focus on two projects. The first one is the multiple convolution project, in which I designed a method that allows us to analyze resonance and room modes in spaces with complex geometries. And then the other project is the Sonic Sculpting project, which is a generative AI approach to design spaces using the impulse response of the room. So I am an assistant professor in architecture, and I also lead the Advanced Acoustic Design Lab in Virginia Tech. To give you a context of my background that led to my interest in analyzing and designing acoustic environments, I started working in renovation projects in a hospital. And then that's when I realized the impact of the indoor environment in human health and well-being, given the sensitive state of the patients in these rooms. And then one of my main tasks was to identify sustainable materials to be used in patient rooms. One of the most challenging areas was, at that time, finding sustainable materials related to or sustainable acoustic solutions. And that's what motivated my work in designing the cymatic sound diffusers, which was intended to design sustainable acoustic solutions. And then I was also interested in the impact of acoustic environments in human well-being and the perceptual and social aspects. After joining IAU as an assistant professor, I joined the MIT Media Lab, working with two groups, the Opera of the Future, focusing on acoustics, and the Affective Computing group, focusing on well-being. So in general, my work focuses on environmental and social challenges given the acoustic environment. I do this through my research and teaching, through engaging with the public, and I'll mention an example of how my project starts through engaging with the public and then identifying some of the challenges and trying to find the solution. So I focus on innovative, sustainable solutions for acoustics, immersive experiences that enhance well-being and social connections, and advanced computational technology that enables designing and analyzing complex acoustic environments. Given the complex challenges that my work addresses, it's interdisciplinary by nature, so it includes architecture, acoustic metamaterial, sustainable environments, immersive technology, machine learning, and design. And I consider acoustics as the thread that connects all these fields. My work has been recognized by MIT Technology Review, and recently I was named as a senior member of the National Academy of Inventors. So how is analyzing and designing complex acoustic environments related to well-being? Resonance. I wanted to understand resonance, analyze it, and recreate it. Room modes have been considered as sound defects, but are they always negative? Room modes are the resonances that amplify sound frequencies and suppress others, and therefore they change the tonal characteristics of the sound. So it has been reported that in some historic and worship spaces, the resulting resonance can provoke an emotional response that enhances the listener's experience. So first, I wanted to understand and analyze this emotional impact, and that's where I will start with the Oral Affect project. This project included multiple phases. The first one was the perceptual and cultural aspects, in which I asked the question, can the acoustic environment impact emotions? And does the cultural background enhance this impact? If yes, then how? How does the acoustic parameters contribute to this impact? What are the characteristics of such spaces that evoke emotional impact? And how does the room interact with the sound source through resonance? And later, I wanted to correlate the emotional indicators with the acoustic metrics. So by asking the question, what are the acoustic characteristics of spaces relating to their emotional impact? And the goal of this was to establish guidelines for designing spaces with supportive acoustic environments. So for the first phase, including the perceptual aspects, I use virtual environments by including the visuals and the acoustic environments. And the reason for including the visuals as well is that my interest was not only in the sound, but in the sound that is created through the architectural elements. So I use binaural recordings, and then to analyze the physiological and psychological aspects. For the physiological aspects, I used biosignals, including heart rate and EDA, skin conductance. And then for the psychological aspects, I use self-report. And then later, I developed a method to analyze resonance in spaces with complex geometries. And that's the physical aspects. And the last stage was creating a correlation between the acoustic metrics and the emotional indicators to understand the role of architectural features in enhancing the acoustic experience. So for the first part, in the perceptual and cultural aspects, the interest was in understanding whether the sound reflections created by the acoustic environments will amplify the emotional impact that will already be created through the musical characteristics of the sound itself. So in this research, I compared the intensity of the emotional impact between wet recordings that included the sound reflections in 4 buildings used as case studies with the dry recording. So this is one of the results of the buildings of the paper. And if you're interested, you can read the whole paper published in Building Acoustics. So we can see here the result of the heart rate. In the dry recording, there is an emotional impact evoked by the musical characteristics of the sound itself. But we can also see with the wet recording, when we include or consider the sound reflections, that emotional impact was intensified. So now we move to the physical aspects and the method for analyzing resonance. So resonance results in amplifying some frequencies and suppressing others, and therefore it changes the tonal characteristics. And then the tonal modification is usually problematic, especially in spaces such as recording studios or concert halls, where we need a consistent acoustic environment or homogeneous acoustic environment. But unlike recording rooms, where achieving this homogeneous acoustics is preferred, having diverse acoustic characteristics at different parts of spaces, such as worship spaces, can be favored. This acoustic variety can produce oral aesthetics, forms auditory symbols, and creates emotional experiences. Therefore, the resonance resulting from the reinforcements of specific frequency bands can provoke an emotional response that enhances the experience. And this amplification can be result from the reflection from the architectural elements, such as dome or the subspaces. And then the reflected sound can be stronger than the direct sound, especially at some frequencies. The acoustic environment results from the room's response to a sound source, depending on the characteristics of the room in which the sound is propagating. This includes the room volume, geometry, and the materials present in this room. And room modes are the resonances that are generated through playing a sound in a room, and they are formed by constructive and destructive interferences caused by the sound reflections. They result in amplifying some frequencies and suppressing others. And this amplification is typically non-uniform, so it will be varied across different frequency bands. So how do we analyze it in spaces with complex geometries? The traditional method includes using this equation that takes into account the room dimensions. But as we mentioned, we want to have a method that allows us to analyze room modes in spaces with complex geometries. We also want, because we mentioned that the acoustic experience is created by the geometry, material, and volumes, and also through the interaction between the room and the sound source. So that was the motivation behind developing the multiple convolution method that allows us to consider the room geometry, materials, the location of the sound source and receiver, and also the source type. This method was inspired by Alvin Lucier's piece, I Am Sitting in a Room, where the composer records his voice and then plays it back into the room, records the playback multiple times until the frequencies within his voice that correspond to the resonances of the room are amplified and then transformed into a ringing of room modes. So let's listen to an example of replicating the same method using simulation. This is the dry recording. This is the first convolution. The second convolution. Third. And fourth. Now we can start to hear the ringing of room modes. So the goal was to use this method to analyze room modes in spaces with complex geometries, such as the building which was used as case study. In this case, it was the Deanna Center of America in Maryland, the DCA. But before that, there was a need to validate the method by comparing it with the results of the traditional method using the equation in a cuboid room. So after validating the method, now we wanted to test the method's ability to allow for accounting for different sound source, the amplification that the room modes will result depending on different sound sources and accounting for the space material, the sound source and receiver location. So if we take a look at the frequency response of the studied room, we can see that if we take a look at the frequencies 319 hertz and 3734 hertz, we can see that the peaks that represent some of the room modes, in this case, the selected ones have equivalent amplitude. But if we convolve the impulse response with a sound source, in this case, I selected pink noise, which has a higher amplitude at low and mid frequencies than high frequencies, we'll see that the amplitude will be different at these two selected frequencies. So why is this important? When we analyze room modes using the traditional method, we will identify the frequencies where the room modes occur. But in order to understand the impact of these room modes depending on the sound source. So for example, let's say if it was a recording room and we want to analyze the impact of room modes when someone is playing the cello with more dominant low frequencies versus the violin with more dominant high frequencies. The room will amplify frequencies, different frequency bands differently depending on the room modes. And that's important in studying the interaction between the room and the sound source. So if we take a look at two different sound sources now and applying the method first provides an amplification or a visualization of the room modes, but also it allows us to understand how different sound sources will be amplified. For example, in the second sound source at the bottom, you can see that there is a dominant frequency range. And in this case, the amplification of the two selected frequencies will be different depending on the dominant frequency of the sound source. So now we wanted to test whether the method will allow us to consider the room materials. So if we go back to the image, we placed sound absorbers at 3 walls of the same cuboid room. And then here using, again, the same 2 sound sources, we can see that looking at the spectrum, after applying the sound absorbers, we can see that the amplitude or the amplification resulting from the room modes was different depending not only on the sound source, but also depending whether we had the sound absorbers or not. So why is this important? This method will allow us to test the amount of sound absorption and also the location of sound absorbers needed in order to achieve the required or the desired acoustic environment, considering the room modes. Now, the sound source and receiver location. So if we apply the method to the case study by changing or testing multiple sound source locations, we can see that depending on the sound source location, the amplified frequencies were different, especially at the high frequency range. So this method will allow us to understand the amplification that will be resulted using here, for example, we have the same sound source 1, but the level of amplification at high frequencies was different depending on the sound source location. So here, the developed method will act as an amplifying glass that allow us to identify room modes while also considering the sound source and receiver location, the room materials, and then the room geometry. So the third part was correlating the acoustic metrics with the emotional indicators. This is a whole paper that if you're interested, you can take a look at JASA, but I'm just sharing here, highlighting the main finding in this paper, in which we realized that the building that was reported as the highest in terms of the emotional impact was also the building with the highest resonance quality at low frequencies. And in this case, the building has distinguished geometry, and that was motivating to study how can we design spaces that enhance the emotional impact or positive emotional impact to create supportive acoustic environments. So all the previous work was focusing on the evaluation, but the next projects will focus on the design aspects, and they're all ongoing projects. The first one is the Sonic Sculpting. So the goal of the Sonic Sculpting project was to develop a generative AI approach to propose geometric solutions based on the acoustic features and mainly the impulse response. Let's first take a look at the traditional design process for spaces where acoustics are essential. Based on my conversation with architects and acoustic consultants, the traditional method starts with the conceptual design by the architect, which then is submitted to the acoustician, which will run the acoustic simulation. So in this case, the process is an iterative process that starts with the design, then evaluating the acoustics, redesigning, and then reevaluating. In this process, we are fixing the acoustics of the design, while what I'm proposing is to design for the acoustics. What if we can design spaces based on the desired acoustic environment? So it's a generative design approach to propose geometric solutions based on the impulse response. And I call this project the Sonic Sculpting. One of the motivations behind this project was finding that although there is a lot of research in machine learning and acoustics, the majority of the projects I came across did not involve acousticians. So in this case, although the tools developed allow for estimating the acoustic environments, the accuracy was not enough for acousticians to use it in the design process. Also, the majority of the projects were focusing on generating the acoustics from the visuals. So let's take a look at some of the examples. The first project is the image to reverb, which was by one of the collaborators of the Sonic Sculpting projects. And in this project, the researchers generated impulse responses from images. In this case, it was just 2D images. So they trained the model by using a database of images of spaces alongside their impulse responses. And then the model was able to predict the impulse response when was given a new image of a new space. So after creating the impulse response, you can use this to create an oralization by convolving the impulse response with an anechoic recording. In their project, they use real spaces with ground truth to validate the method, but the application extended to use for virtual spaces. This includes video game scenes, paintings, and AI-generated images. And one of their examples was to predict the acoustic environment of the International Space Station, which is a space that we cannot visit or listen to its acoustic environments typically. Another project is the neural acoustic fields, in which the researchers generated continuous acoustic representations to be used for video games and VR applications as a walkthrough oral experience. Third project is Mesh to IR, in which the researchers generated impulse responses for indoor 3D scenes represented in meshes. So we started from 2D, and now this project includes 3D scenes. But all the previous projects focused on generating the oral experiences from the visuals, while our focus is to generate the visuals or the 3D geometry from the acoustic experience or the desired acoustic experience using the impulse response. There has been some theoretical work in this area, including this project titled Can One Hear the Shape of a Room? In this case, the researchers estimated the room geometry from the room impulse using the image source method. They started with 2D, but then they also included 3D. Some of the considerations for this project includes, in order to train the model, you need a large data set. So we had the geometric wave acoustic data set, which includes 3D models and impulse responses, mostly for residential buildings. And the impulse response was generated using a hybrid simulation, including wave-based and geometric simulation. One of the limitations of this data set was that it's very homogeneous. So majority of, if not most, all the buildings were residential buildings. It included multiple spaces, and it also included furniture. So our approach was considering to use this data set for the pre-training, given that we have a large data set, but then using higher quality simulation used by acousticians, such as some of the models in Audion for the fine-tuning stage. In this case, we're using it for the fine-tuning and not the training because we had limited number of models. But recently, with the release of Dribble SDK, we're considering to generate the data and also train the model using the same platform. So that opened a new possibility. Another challenge is the diversity in room characteristics. So whether to consider geometry, volume, and materials. And we considered in this project to focus on the geometry, considering the volume as well. But the materials will be considered in future research. Third challenge is the many-to-many relationship. In this case, even if we have the same geometry, the impulse response will depend on the location of the sound source and the receiver. So if we use the model to predict the room geometry using impulse response at different locations, we want to ensure that we reconstruct the same geometry. Another challenge is what kind of 3D representation to use for the model, the visuals. So we considered point cloud, voxels, and meshes, and then we selected meshes as the gold standard for the training. So the initial approach is we're converting the meshes into signed distance fields and use the multi-layer perception decoder conditioned on audio to predict the signed distance field. Then the audio is encoded into a conditioning vector by encoded that trains alongside the generator, and then the resulting signed distance field are then reconstructed into 3D meshes. As I mentioned at the beginning of this project, the motivation was to use it as a tool during the conceptual design stages for room acoustic design to propose multiple 3D geometries that achieve similar acoustic or desired acoustic environment. But we see also potential for applying this project in virtual acoustic environments, VR, AR, and video games. Another application is to use it for environmental sensing. In this case, because we are reconstructing the 3D environment, it can help in the navigation indoors for robots and also outdoors for autonomous vehicles. The difference between the two applications is that in this application, we need to reconstruct the exact environment. While for room acoustic design, there is the possibility to generate multiple design solutions. So I want you to keep this question in your mind while I present the last project, considering the environmental and social challenges related to acoustics. How can we use generative AI in designing sustainable and supportive acoustic environments? And the interest in designing supportive acoustic environments after analyzing the emotional impact of acoustic environments in our experiences, I wanted to find a way to design supportive acoustic environments. Considering that humans have always interacted with acoustic environments to enhance well-being through either rituals, worship, meditation, and so on. So that was the motivation behind the Sound Escape project, designing supportive acoustic environments that enhance well-being. So the name of the project came from the word soundscape and also the two words sound and escape. In this project, we explore how acoustic environments can elicit the emotions of awe and wonder in order to create a restorative environment that supports well-being. This was built on the attention restoration theory in environmental psychology, which focuses on enhancing well-being through soft fascination. So soft fascination is to create a stimulus that is engaging, immersive, but at the same time is not overstimulating. And the majority of work in the attention restoration theory, at least at the early stages, was focused on visuals. There has been some recent research in acoustics, and but even within acoustics, the majority of the research is in the outdoor soundscape. And I was interested in finding a way to use the interaction with the acoustic environment as a coping mechanism to enhance well-being. So the goal is to enhance the well-being for the general public, but also the long-term goal is to provide a coping mechanism for neurodivergent individuals so they can thrive, especially individuals with ADHD, given that their main challenge is related to attention. And applying this theory, it is focused on enhancing attention through attention restoration. So at the early stage of this project, I participated in an event at the MIT Museum titled Meditation, Art, and Neuroscience in Conversation, in which we had a psychologist and a monk. And then I asked one of the participants to interact with an acoustic environment through oralization, through spontaneous humming. And then I played back the humming and I asked the audience members to hum together with it. And then we asked them to reflect on their experiences. So they mentioned a lot of interesting reflections, but the ones that stood out to me were including losing sense of space because they were interacting with an acoustic environment of a different space, but also losing sense of time. So one of the participants mentioned that they lost sense of time because of the interaction with the played back humming that was included, that included the oralization. And then the monk mentioned that this is usually part of the meditation practice in which people repeat the mantra. And then one of the interpretation of this is that through the reverberation, people are listening to the sound of now and the sound of few milliseconds ago. So that contributes to losing sense of time. And also one of the audience members mentioned that they were outside of their heads, so losing sense of self. So what made these three reflections stand out is the comment by the psychologist when she mentioned that those are the three pillars of meditation: losing sense of self, losing sense of time, and losing sense of space. So I thought that there might be a great potential to apply this project in creating a restorative tool for people through interacting with the acoustic environment. So first, I wanted to identify the psychoacoustic characteristics that can be used in designing soundscapes that lead to restorative experiences and then enhance well-being. So we used an existing data set that includes some soundscapes and then the emotional or the affective response to the soundscapes, in addition to the psychoacoustic metrics of the soundscapes used in the study. The psychoacoustic metrics included sharpness, fluctuation strength, and roughness. And the affective response included pleasant, eventful, annoying, and uneventful, which corresponds to the Russell model of emotions that includes emotional arousal and valence. So after analyzing the data set, we realized that considering the psychoacoustic metrics you can see here in sharpness, fluctuation strength, and roughness, the affective response that correlated the highest with these acoustic metrics, psychoacoustic metrics, were the ones related to negative affective response. So in this case, it seemed that this high correlation would be beneficial in reducing negative affective response in soundscapes, but not necessarily as useful in designing a positive affective response in designing soundscapes. So we wanted to find new metrics that allow us to design spaces that that support well-being and enhance positive emotions. And one of the main aspects that we wanted to consider is the interaction with the acoustic environment, because the majority of previous work in this area in soundscape and well-being was through passively listening to soundscape that considered as a positive soundscape. But how about interacting with the acoustic environment, which was the traditional practice that humans have been interested in? So Megan Wysocki, my student, is currently working on this project in which she is applying real-time oralization with an acoustic environment with the goal of provoking or evoking positive emotional impact. If we consider the Russell model of emotions, we wanted to reach that soft fascination that I talked about in the attention restoration theory. And we are hypothesizing that it's going to be in this area between positive valence but not too high arousal. We have similar to these sleeping pods at Virginia Tech. So we were thinking, what if we can apply this tool within these sleeping pods to use them not only just for sleeping and relaxing, but also as a restorative space through the interaction with the acoustic environment. So in that case, can be used in offices, in airports, or even in schools. So what we are considering now is to collect impulse responses and manipulate some of the characteristics based on, after identifying this, considering the psychoacoustic metrics from the previous study, and then using it as a stimulus, then measuring the attention restoration and also EEG. So we were hoping to use the Neurable headphones, which is a headphone that includes EEG measurements to measure the potential of the acoustic environments in enhancing well-being through attention restoration. So in this case, we expose the participants to, first we measure their attention, then we expose them to a stressor, and then we expose them to the stimulus, then measure their attention, and then ask them for a self-report. This is still an ongoing project. So this is just an example of the tool that we are using to manipulate the characteristics of the acoustic environment or the impulse response through the real-time oralization.
Production methods. So for example, we can have a high pass. It's actually not quite noticeable on this one. But if we start to say we reduce or increase the gain of the higher frequencies, production.
So other students have been trying to identify what kind of packages within the Mac software to use that corresponds to some of the psychoacoustic metrics in the ISO standards. So Hector was working on that section. Hector received the Outstanding Europe Award at MIT, and Ali Hong and Jean Yu presented this work previously at the Internoise as part of the Flash Talk Challenge. So I just wanted to acknowledge their contribution. Also, this research received the IBK Research Award at MIT a few months ago. And now we go back to the same question, considering the environmental and social challenges. How can we use generative AI in designing sustainable and supportive acoustic environments? I would be happy to answer your questions and hear your thoughts in that aspect. Thank you.